Welcome viewers to this new session on algebraic structures. In the previous session we have talked about subgroups. In this session we will talk about an extension of the subgroup or something that is defined by using the subgroup, that is the coset. So let's begin. By definition, let H be a subgroup of G, and if let us say A is any element of G. Now when I say H is a subgroup of G, what I mean is that G comma dot is a group and H is a subset of G, and H comma dot is a group by itself. Let H be a subgroup of G and let A belongs to G. Let A be any element of G, then the set that is defined by HA. That means all the elements of H operated upon on the right hand side by the chosen element from G is called the right coset. Similarly, the set AH defined by taking all the elements of H and operating them on the left hand side by the chosen element from G is called the left coset generated by H and A. Now, both AH and HA, both the left and right cosets are subsets of G. We also know that the identity element of G and the identity element of H is same. Right? And identity element, any element you operate upon with the identity element remains the same. That means the left coset generated by identity element will be the same as the subgroup H, which will be same as the set HE. Why? Because any element of H you operate either on left hand side or right hand side by the identity element will not change. So that means the subset H itself is a right as well as a left coset. Another important point, if G is abelian, that means if the dot operation is commutative, then the left coset and the right coset will be same because HA and AH will be same. So let's take an example. If you see the definition carefully, you will understand that the coset is actually being defined by the subset and the element A from G. So that means the number of cosets that can be defined is equal to the size of G. Every element of G is defining a new coset. So the number of elements in G will be the equal to the number of cosets that are defined. Similarly, what will be the size of the coset? See, how am I defining the coset? I am taking the element A from G and operating with all the elements of H. So the size of the coset will be same as the size of H. Let's take an example. Let us take the group G as 0 to the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8 and the operation as addition modulo 9. Remember, addition modulo 9 means I'll add the two numbers, take the result, divide it by 9 and take the remainder. And let us say the subset has been defined as 0, 3, 6. Right? Now, as there are 9 elements in the group, so a total of 9 cosets will be defined. Addition operation, I know by definition is commutative, so I am only talking about the left cosets. The right cosets will be same. The only difference will be if I am saying 0 plus H, the right coset will be H plus 0. So let's define the 9 cosets. 0 plus H. So what I am doing is I am taking this element 0 and operating it on H. So I have the three elements 0 plus 0, 0 plus 3, 0 plus 6, which is same as 0, 3, 6. Similarly, the coset defined by 1, I'll get 1, 4, 7. 1 plus 0, 1 plus 3, 1 plus 6. Similarly, coset defined by 2, I'll get 2, 5, 8. Then coset defined by 3, it will be 3 plus 0, 3 plus 3, 3 plus 6. So 3, 6 and 3 plus 6 will be 9, which in mod 9 will be 0. Similarly, the coset defined by 4 will be 4, 7, 1. Coset defined by 5 will be 5, 8 and 2. 5 plus 6 is 11. 11 in mod 9 is 2. Similarly, coset defined by 6 is 603. Coset defined by 7 is 714. Coset defined by 8 is 825. Notice something? Not all cosets are unique. You can see the coset 0 plus h, the coset 3 plus h, and the coset 6 plus h. They are essentially same. Please remember, in a set, the order of elements does not matter. So, the set 036, the set 360, and the set 603 are all same. Similarly, the coset 1 plus h, same as coset 4 plus h, same as coset 7 plus h. Similarly, the coset 2 plus h is same as coset 5 plus h, which is same as coset 8 plus h. Right? So, not all cosets are unique. Keep this in mind. We have a very important theorem based on a concept related to this. Let's take another example. Let's say this is the set that has been defined 1, 7, 11, 13, 17, 19, 23, 29, and we have the subset 1 and 11. This is actually, these are all the prime numbers under 30. So this is actually a set denoted by U30. So the operation is multiplication modulo 30. Remember, number of cosets is equal to size of group, and size of coset is equal to size of subset. So I will have, how many elements are there in the group? 1, 2, 3, 4, 5, 6, 7, 8. I will have 8 cosets. Let's identify them. So the coset will be defined. See, the operation here is multiplication. So I'll write 1h, 7h, 11h, 13h, 17h, 19h, 23h, 29h, and so on. The operation is multiplication modulo 30. That means two numbers will be multiplied, the result will be divided by 30, and the remainder will be taken. So 1h, now I'll take elements from G. 1h is equal to 1 and 11, 1 multiplied by 1 and 1 multiplied by 11. 7h is 7 multiplied by 1 and 7 multiplied by 11, that is 777, and now 77 in mod 30 reduces to 70. 32 is 60 and remainder is 70. Similarly, 11h is 11 and 121, 11 ones are 11 and 11 11s are 121, reducing it I get 11 and 1. 13h is 13 and 143, which reduces to 1323. Similarly, 17h is 17.7, 19h is 19.29, 23h is 23.13, 29h is 29.19. Once again, see, 1h and 11h are same, 7h and 17h are same, 13h and 23h are same, and similarly 19h and 29h are same. Let us see certain properties of cosets. Now, in order to better understand the properties of cosets, I have shown both the examples that we solved earlier. I have shown both the examples over here. So what we are going to do is we are going to take each property and verify whether this property is shown over in these examples or not. So the first property says that the element A that is being used to define the coset belongs to the coset itself. Let us see. The one element which is being used to define the coset belongs to 1h, 7 belongs to 7h, 11 belongs to 11h, 13 belongs to 13h, 0 belongs to 0 plus h, 1 belongs to 1 plus h, 2 belongs to 2 plus h. So the first property is satisfied. If the element A, see, A is actually the element of G. If the element A also belongs to H, then AH is equal to H. If I see this case, the H has three elements 0, 3 and 6. So by this property, if 0, 3 or 6 is being used to define the coset, then that coset must be equal to H. Let us see. 0 plus H, same. 3 plus H, 360, and 6 plus H is 603. Similarly, if I see over here, in this case, H was 1 and 11. So 1H and 11H are both same as H. AH is equal to BH, or AH intersection BH is equal to 5. What it means is the cosets, either the cosets will be same or they will be disjoint. Let us see. See, 1H and 11H are same. But if you see, 1H Except for 11H, no element of 1H is present in any of the other cosets. Similarly, if you see 7H, except for 17H, no element of 7H is present in any other cosets. So the two cosets, if I take any two cosets, they'll be either same or disjoint. Similarly, you can see over here 0 plus H, 3 plus H, 6 plus H are same. But 0 plus H, see, there are essentially three unique cosets over here, 0, 3, 6, 1, 4, 7, 2, 5, 8. You can clearly see that they are disjoint. Another important thing, the distinct cosets form a partition of G. Partition of G means they will be disjoint in themselves and their union will give me the complete set G. See, if I take the union of 0 plus H, 1 plus H and 2 plus H, I get all the elements of G, 0, 1, 2, 3, 4, 5, 6, 7, 8. So all the elements of G I can get over here. Similarly, what are the unique cosets over here? 1 plus H, 1H, 7H, 13H, 19H, 1H, 7H, 13H and 19H. If I take the elements from here and I take the union, I'll get the original set back. So all the properties are verified. Another important point, if you see how many distinct cosets are there? 4. How many distinct cosets are here? 3. Now let us see a theorem that has been defined on cosets. Lagrange's theorem. Lagrange's theorem says if G is a finite group, remember it is only defined on finite groups, and H is a subgroup of G, then order of H, remember order of a group means number of elements in that group, then order of H divides order of G. In other words, order of G will always be a multiple of order of H. See, if you see over here in the previous examples, 036 was a subgroup of G. There were 9 elements over here, 3 elements over here. And in this example, there were a total of, if you see, there were a total of 1, 2, 3, 4, 5, 6, 7, 8. 8 elements in the group and 2 elements in the subgroup. So this property is satisfied in these examples, but we are going to see that this is true for any cases. Then the number of distinct left or right cosets of H in G is order of G divided by order of H. Let's first verify it from the examples. Over here, order of group is 9, order of subgroup is 3. So 9 divided by 3 gives me 3 distinct cosets. Again, in this case, order of group was 8 and order of subgroup was 2. So number of distinct cosets is 4. 8 divided by 2, 4. So this theorem is being verified by these two examples. Now let us prove this theorem. Let H be a subgroup of order M of a finite group G of order N. Let us say the group has an order N and the subgroup has an order M. So obviously N will be greater than equal to M. The order of the group will be either greater than, because H is a subset of G. Now let us say H, let us try to define H. Let us say the elements of H are H1, H2 up to Hm. These are the M distinct elements of H, because if they are not distinct, then the order of H cannot be M. Remember, if there is an element that is repeated in a set, it is counted only a single time. Let A belonging to G be the element which I am using to define the coset, then AH is the left coset of H in G. Now AH will be defined as AH1, AH2, AH3. What I am doing is I am taking the element A and operating all the elements of H on the left hand side with A. I am explaining this theorem on the basis of left cosets, but all the explanations, the entire description can also be written in terms of right cosets. Just simply replace left by right, AH by HA. Simply where I am writing AH1, you will write H1A and so on, and this entire description will fit the right coset also. Now these elements that I am getting AH1, AH2, AH3 up to AHM, they are also M distinct elements. See, obviously these are M elements and moreover they are distinct elements, as let us assume that they are not distinct. Let us say there are two elements AHI and AHJ which are same, where I is not equal to J. If AHI is equal to AHJ, then by cancellation law, these are groups and subgroups. So by cancellation law, I can cancel A and A from here. So I'll get HI is equal to HJ, which goes against my original assumption. My original assumption was H1 and H2 up to HM are distinct elements. So AH has M distinct elements. In fact, every left coset of H in G has M distinct elements. So let's proceed. Now, as G is a finite group, G is a finite group. That means the number of elements is G in G is finite. So the number of left cosets is also finite. And so the number of distinct left cosets is also finite. As G is a finite group, the number of left cosets is finite, and so the number of distinct left cosets is also finite. Let us say I have k distinct left cosets, and let us say the elements that are being generated that are being used to generate these distinct left cosets are A1, A2, A3 up to AK. So the distinct cosets are A1H, A2H up to AKH. Now all these distinct cosets, see by the properties that we have already seen, all these distinct cosets are disjoint and their union is equal to G because they create a partition of G. So A1H union A2H and so on up to AKH is equal to G. As the union of all these elements is equal to G and they are disjoint in themselves. How? We have already shown that there are M elements in this, M elements in this, M elements in this, and it had N elements. And moreover, all these elements are unique or distinct. They are all pairwise disjoint. So order of G is equal to order of A1H plus order of A2H up to order of AKH. None of the elements here is common. So order of group was N. I can write M plus M up to M k number of times. So N is equal to Mk, or order of G group is equal to K multiplied by order of H. As K is an integer, you can only have 3, let us say 3 or 4 or 5 or 6 distinct cosets. You can never have 3.2 distinct cosets. So K is an integer. So order of subgroup divides order of group, or in other words, order of group is a multiple of order of subgroup. So the first part of Lagrange's theorem is verified. Now proceeding further, the number of distinct cosets, remember we assumed it to be K. K is equal to order of group divided by order of subgroup. So the second part of Lagrange's theorem is also verified. So this essentially finishes our discussions on group. Right? If there are any doubts, any queries, you can post them in the discussion session or you can post them as comments and we'll get back to you. Thank you.